Hi Math 1, let's take a look at task 2.1. This unit is going to deal a lot with the things that we studied last chapter. Okay, so we have a linear function or an exponential function. So we have some new words, but we're going to have a lot of the same ideas happen. My little sister Savannah has a piggy bank. She started with 5 pennies, and each day when I come home from school, I give her 3 more. So let's take a look at the tables. They've got it started here for us. So we've got days. Okay, each day I give her 3 more pennies. She started with 5. Okay, that's why there's a 0 there. So we've got 5 pennies. And if I add 3, that makes 8. And each day we add 3 more, 11, 14, 17. So let's go ahead and make a graph. The first thing I'm going to do is make sure that I label the x-axis with the word days. And then let's label the y-axis, okay, pennies. So we've got some pennies that are going to be going up higher. So at first, there's 5. Day 1, she's up to 8 pennies because I gave her 3. Day 2, we're up to 11. Day 3, we have 14. And day 4, 17 pennies. Okay, let's describe the sequence. Okay, we are going to be an arithmetic sequence. Okay, and the reason is we're adding 3 each time. We're adding 3 each time. Let's go ahead and write an explicit equation for this. So we're going to call it f of x. And you always start with the starting value, which is 5. And then the pattern, which happens to be plus 3. And then we have to figure out how many times we're going to do that. Since this table has a 0, we just put an x. Okay, let's keep going. Example number 2. At the end of the summer, I decided to drain my pool. The pool started with 100 gallons of water. Okay, there's the starting number, 100 gallons of water. Okay, and the hose was draining the pool. Okay, draining means that you're going to be losing water. If you are losing water, it's going to be decreasing at the rate of 4 gallons every minute. So we're going to go ahead and subtract 4. That would make 96. Subtract 4, 92, 88, and 84. Okay, when you make your graph, let's go ahead and look at the x value. So we've got some minutes happening here. Minutes, 1, 2, 3, 4 minutes. And then the y-axis is gallons. Okay, gallons. So there's definitely something different happening here with the gallons versus the pennies. Okay, so we start at 0, 100 gallons of water. And then since the pool is draining and losing water, we only go to 96. Minute 2 takes us to 92. Minute 3, 88. And then 84. Okay. Now this is a pool. This is a pool of water. So I know that there was 100 gallons at the beginning, and I know there was 96 gallons after 1 minute. Do you think the pool ever had 98 gallons? Well, of course it did. The pool is draining. So in order for it to lose 4 gallons, it had to have 99, 98, 97. So what's different about these is this example, okay, we are going to connect the dots. We are going to connect the dots, and we're going to draw a line through this. What? Well, how come we didn't draw the line up here? Okay, she had 5 pennies. The first day, I gave her 3. She had 8. I never gave her 1 penny. I went straight to 8. Then when I gave her 3 more pennies, she suddenly had 11. she never had 9 pennies. Okay, so there is a slight difference here. Pennies are something we count. Okay, so pennies we count. If we count something, then we're going to leave it as dots. Okay? But when you're talking about something like water, okay, if it's something that we measure water, okay, that is something that we're going to connect. Okay, we are going to take some notes on this in just a second. This sequence, okay, is arithmetic, and it's arithmetic because we are subtracting. We are subtracting 4 each time. Okay, so it is a straight line, but it's connected. Let's write an explicit equation for this. F of x equals, let's go ahead and start with 100 gallons of water. And then the pattern is -4. And since this table starts at 0, it's just going to be x. Okay, let's go to the next page. Are you taking good notes? My sister started with 5 pennies in her piggy bank. Okay, and each day the number of pennies doubles. Ooh, doubles. Okay, that's an important word. So doubles means multiply by 2. It can also say the word twice. Okay, so we start with 5 pennies, just like last time, but now the pattern is multiply by 2 each day. So 5 times 2 is 10, 10 times 2 is 20, 40, 80. Wow, that's a lot of pennies. Okay, but that's what happens when you have a multiply pattern, right? Days is going to go on the x-axis, and then pennies is going to go on the y-axis. Okay, there's these pennies again. All right, let's make our graph. So we start with 5, 0, 5, 1, 10, 2, 20, 20 right in the middle right here, 3, 40. Wow, 40 got big, right? Remember, when you multiply, it's supposed to look like a curve. 4 takes us up to 80. Yep, definitely a curve. Okay, now the question is, should I connect them? I know she had 5 pennies, then she had 10 pennies. Did she ever have 8 pennies? No. Okay, remember, this is something that we count, so you leave it like dots. Okay, this is geometric because the pattern was multiply by 2. The explicit equation, f of x. Okay, we started with 5. Start with 5. Oh, geometric. Remember, geometric is a multiply pattern. It's times by 2. And geometric get exponents. It's just going to be the power of x since we have a 0. Okay, remember, let's just write down. Geometric get exponents. They get exponents, okay? And this one we leave as dots because we're counting pennies. Okay, let's take a look at this problem. At the end of the summer, I decide to drain my kiddie pool, okay? Drain means that you're going to decrease. Okay, you're going to drain your pool. Okay, it's going to go down. It's going to go down. So it starts with 200 gallons. And I notice after each minute, there was only half. There was only half. Okay, so we're going to multiply by half. Each minute, we're going to multiply by half. So half of 200 is 100. Half of 100 is 50. Half of 50 is 25. And half of 25 is 12.5. All right, remember, whenever you draw a graph, start with the labels. So the x-axis is going to represent minutes. Okay, well, there's no numbers here. Let's add an x-axis, and let's add 1 2, 3, 4, 5. The y-axis, okay, I'm going to call gallons. I'm going to call it gallons. Okay, please draw a y-axis. Let's go ahead and figure out our scaling. Okay, remember for scaling, the biggest number I need to fit is 200. So I'm going to take 200 and I'm going to divide it by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, it's got 12 boxes again. 200 divided by 12 boxes. Let's see what that makes. 200 divided by 12 is 16.6. Okay, but that's not nice. We are going to round up. Why don't we round up to 20? 20, 40, 60, 80, 100. 120, 140, 160, 180, 200. Okay, that fit perfectly. 0 takes us to 200. 1 takes us to 100. 2 takes us to 50. 3, 25. 4, 12.5. Okay, so it is looking like a curve, okay, which makes sense when you have a multiply or divide pattern. So it's geometric, and I'm going to say it is multiply by 1/2, and the graph, okay, the graph is a curve. Okay, now the question is, should I connect these? The pool started with 200, and then it got to 100. Did the pool ever have 150 as the water drained out? The answer is yes. Okay, since we measure water, measure means you connect. Okay, so we're going to go ahead and connect this. We're going to kind of go like this a little bit to the left. Okay, and then when you do geometric, all right, be careful here. We don't go down. Okay, what happens is it gets smaller, smaller, almost like you're landing the plane. Closer, closer, you flatten out along that road right there. You do not cross the x-axis. Okay, and that's how you draw a geometric curve. Let's write the explicit equation for this. It started with 200. The pattern was multiply by 1/2. Okay, don't put a multiplier, an X sign there. Put parentheses. And since this is geometric, I'm going to put an exponent of x, okay, and nothing else since the table started at 0. All right, so some things are very similar to our first chapter, but we have this idea of, do I connect it or not? All right, so let's go ahead and write down some official notes here on the next page. Okay. So some of these words are going to be new, okay, but you know what's going on. Okay, so a linear function. The graph looks like a line. Okay, the sequence is arithmetic. So we used to call it arithmetic, okay, but the new word now is linear, okay, because it makes the line. Look, it's right there, line. Okay, it's an adding or subtracting pattern, and we call it the common difference. All right, but there's also a new word, a little star here, okay? They call it the constant rate of change. The constant rate of change, okay? You keep adding pennies, constantly adding 3. What would it look like, okay? A graph that is linear, okay, is going to look like a line. So maybe it is going downhill, like that. Maybe it's connected, or maybe it's going uphill, and it's dots. Okay, but it's definitely a line. All right, let's talk about the next kind. Okay, exponential. Now, we used to call these geometric. Okay, now we're going to call them exponential. So the graph looks like a curve. The pattern is multiplying or dividing. So we used to call them geometric, okay, but now we're going to see the word exponential. Okay, but remember, in their equations, they have exponents, right? They call this the common ratio, okay? Or sometimes they call it the constant ratio. So you might be seeing these words constant a little bit more this chapter. Now, what would the graph look like if it's exponential? Okay, maybe it's connected. Okay, curvy up. Okay, remember, you gotta land the plane. Or maybe it's curvy down, or maybe it's dots. Okay, but the important thing is the graph is a curve. Okay. Let's go back and look at our 4 examples, and let's call it either linear, okay, because it was a line, linear, or we'll call it exponential. Okay, let's go back and see. Our first example. Oops, where's my paper? Our first example here, okay, was this first piggy bank linear or exponential? Okay, and the answer is linear. And we're going to add the words constant rate of change. Constant rate of change. Okay. The second example here. Oh, this one was also linear. Linear because it made a line. Linear, and it's a constant rate of change. Okay. What was the constant rate of change? Oh, -4. Okay. It constantly went down 4. The constant rate of change here was adding 3. Okay, it constantly added 3 to the piggy bank. All right, how about example 3? How about this one right here? Was this linear or was this exponential? Let's switch to the blue pen. This one, since it's curvy, is exponential. Exponential. Okay, you could see right there was an exponent. And we call this a constant ratio. What was the constant ratio? Times 2. Okay, times 2. Multiply by 2. It constantly got twice as many. Okay, and then this one right here, this one is exponential. It's exponential because I see a curve. Exponential. It has a constant ratio. What was the constant ratio? Oh, it was constantly 1/2. Multiply by 1/2. Okay, let's go back to our notes. A discrete function. Okay, a discrete function. I'm going to switch colors here. It describes something that we count. Something that we count. Okay, so it's discrete if it's something we count. Okay, and then you draw dots. So what would that look like? Well, it could be linear and be dots, or it could be exponential, okay? But the important thing for discrete is that you see dots. All right, what about the other kind? What if it's continuous? Okay, then the graph would look connected, and it's something we measure, something that we measure. Okay, so what would the graph look like? Well, it could be linear or exponential, but the important thing, okay, is that the graph is connected. Okay, let's go back and let's label them either as discrete. Discrete means that you see dots, okay, or we'll label it as continuous. Continuous means connected. Okay, let's go see. Example 1. Was this one here discrete or continuous? Definitely discrete. What color did I say I was going to use? Red. This one is discrete. Okay, I know that because I see dots. And it is something that we count. Okay. Is this one here discrete or continuous? Since it's connected, we're going to call it continuous. Continuous. Example 3. Was example 3 discrete or continuous? Since it's dots, we're going to call it discrete. Discrete, okay? And example 4 right here, since it was connected, we call it continuous. Okay. One more bit of information here. Okay, something else you can look at is if the function is increasing. Okay, if it's increasing, that means it's going up. It's going up from left to right. So maybe it's dots going up. Maybe it's a curve going up. Maybe it's connected but going up. Maybe it's exponential, okay? But the important thing, okay, is that it's going up. It's increasing, okay, from left to right. From left to right. All right. What about a decreasing function? A decreasing function. So a decreasing function, d, okay, is going down, okay, from left to right. From left to right. So maybe it's going down, down, down with dots. Maybe it's connected, okay, but going down. Maybe it's exponentially going down. Maybe it's curved, okay, but from left to right, it's decreasing if it's going down. All right, let's go back for the last time and let's label them either increasing, okay, or decreasing. All right, example 1. Example 1. Would this be increase or decrease? Since it's going up, this is increase. It's an increasing. The pennies are going up. I could also look here and tell you it's going up, right? What's happening here? The water is going down. Look, it's going down. The numbers are going down, down. This one is decrease. It's a decreasing function. Example 3. Example 3. These pennies, I had 5. Then I have, oh my gosh, 40, 80. This is an increasing function. An increasing function. Okay, the numbers are definitely getting bigger. And example 4, okay, example 4 is a decreasing function. Decreasing, the numbers are going down. Okay, so there's lots of vocabulary here to start off with this second chapter. Okay, so hopefully you have a good page of notes here to reference. The last thing I need to talk to you about is combining like terms. Okay, so combining like terms, okay, combining like terms helps us simplify an expression. Okay, it's going to make it smaller. Like terms have to have the exact same variable. The exact same variable. You can put things together, okay, if they are alike. Okay, so let's look at this example here. And if you have some colors, play along with me. I see a 3x. Okay, I'm going to give him a little green line. Oh, and I noticed that there's an x down here. Okay, now something you have to make sure you do is you look in front. You have to look in front to know the sign. Okay, if you don't see anything, is that a negative? No, that's a positive. That's a positive. I'm going to combine these x's together. Okay, and you can use your calculator to help you. So what I think I'm going to do is type a 3, and then that's minus 5. So I'm going to put these x's together. 3 minus 5, and that's going to make negative 2x. Negative 2x. All right, let's go ahead and look for another letter now. I'm going to look for some y's. Oh, I see some y's right here. I'm going to give them 2 lines, okay? And he's a positive 2. He's not negative. Oh, and then here's some y, so let's put these ones together. That's a 2 plus a 6. 2 plus 6 makes 8. A positive 8, not a negative 8, so I'm going to say plus 8y. Okay? And then finally, I notice that there's this number here. There's no other plain numbers. Okay, so I'm just going to write him by himself. Drop it down, plus 9. Okay, so you can use lines, you can use colors. Some people even use circles. Let me show you one with circles. Number 1 right here. Okay, I see 12x. Well, 12x isn't like anybody else. Okay, so I'm just going to drop it down. Drop it like it's hot. Okay. And then we're going to see this is a negative 8, and this is a negative 12. Those are minus signs, but they're also negative signs. So I'm going to type negative 8. I'd have to type minus 12. Okay, and that's negative 20. Negative 20. I put the numbers together. Some people like to type negative 8 and then and a negative 12. They would add these 2 terms together. That would also give you negative 20. Number 2. I see some m's. Let's put our m's together. Here's 9 m's. And how many m's is that? That's just 1 m all by himself. That's 1 lonely m. 1 m all by himself. Some people like to say, oh, there's 1 m. Okay, but 9 m's here and 1 more m there together are going to make 10 m's, right? 10 m's. And then for the number, we have negative 10 and a negative 3. That's a lot of negatives. That's going to make negative 13. Last couple. Let's combine like terms. Okay, so I noticed that there's some x's here and x's here. Okay, we're going to combine them. Maybe I'll use my calculator. Negative 2 x's are there, plus 6. Let's combine them, and that makes how many? Well, that makes 4. 4 x's. Make sure you type the x. And then the 11, he's a number, but there's no other numbers to go with him, so we'll just say plus 11. Okay. Number 4. Let's see. Let's do our x's. Here's some x's. Here's some x's. Look how I circle the sign that goes in front. So he is a negative, and that's a positive. Let's use our calculator here. Negative 3 is going to get added to 15. And so we have 12 x's. Okay, and then let's add negative 9. Negative 9 plus 14, and that makes a 5. Great job, Math 1.